So horizontal straight line and a point are given. Okay, so the line is given AB. Okay, so AB line is given, and point K is given. So capital letters, you see. So here you can see the projection of it. So on the plane H, okay, so that's the parallel to the H. So that's why the line is straight like this. And in vertical, in profile projection also, that is a straight. And the point, you see, given like K dash, K double dash, and K itself. So the rule is, if the point in the 3D space, if in the 3D space in real life, if the point doesn't belong to the line, in their projection, some of their projection will not lie on the projected line. Okay, so if the K point, you see, it doesn't lie in one, okay, in reality, in real line with capital character. So, but in their projection, it lies, because if you see from the top, you will see it lies in some of the projections, but some of them is not, because the height of the point K is higher than position of AB. Okay, so that means if in any projection it doesn't lie, so that means that point doesn't lie in real 3D space. Okay, understood? Okay, so here another projection. So this line is parallel to the horizontal plane, this one. So these two lines are parallel to the horizontal, and the parallel to the frontal projection, frontal straight line, we call frontal straight line. That is a horizontal straight line if the line is parallel to the horizontal plane. If the line is parallel to the vertical, okay, frontal plane, V plane, so we call frontal straight line. Okay, so it's like this. So we project it to the V plane with slope. But if you see from the top, that is parallel to the V plane, so that's why it makes like this. Okay, parallel line to the XO line. And from the side also, if you see from this side to the W plane side, so you will see again the straight line like this. So because of that is a parallel, the line is parallel to the V plane, so V plane. So that's why it looks like this. Okay, so only one slope. It has only one slope. And again, for the M doesn't belong. So M point in the space is not belong to CD line. So that's why in their projection, you see, it doesn't lie in their projected line also. So if the line is parallel to the W plane, that is profile plane, it looks like as a projection. Okay, orthographic projection. It looks like this. Okay, so the W is here, so that's why it's a parallel to the E dash F dash, and same like E and F line is parallel to the OY and OYH plane. Only one side is it has a slope, so that's why we call profile straight line. Okay, so if you have 3 points, what will happen if you if the 3 points are given in the space? So 3 points are given. So normally you will have a line, the line OX, and in the reality we have something like this. Three points are given. 1 point, okay, so that is X, and O is here. So this distance is and then from the O You have to measure the distance from the O, the first one, and put that distance here. Find a point, and then make parallel line to the OY point, OY line, and then put that second distance to here, and make a parallel line to the OZ, and then define a point A. Okay, so point A is given like this. Point B can be given like okay, so measure that distance, the third one, and that is less than first point, so that's why you can make a like this line. And then B is higher position than A, so point B is here. And then point C is not far from O point, but smaller. So point C is here. So in the space, if the A point and B capital and C capital points are given, so that's in the 3D space. In the 2D space or orthographic projection, orthogonal projection, it will be something like this. Okay, so on the top of OX, A dash, B dash, and C dash are given, and in the bottom, A, B, C small, so it's given, and then in between there will be a line. It might be continuous line or dash line. So that means 3 points are given. So if in examination it's asked like, okay, so how many points you can see? So you have to answer only 3 points, 3 different okay, discrete points are given. Okay, so not 6 points. Okay, so that is 3 points. So 3 points in 2 projection planes makes 6 projections. Okay, but that will generate only 3 points. Okay. So if you connect A and B, so you can generate one line and 1 point is given, are given. So 2 parallel lines can be given like this. So this is in 3D space. So this one, because capital characters. Okay, so A, B, big, C, D, capital, big. Okay, so those are in 3D. So their projection are this. Those are projection. Those are projections, that is in 3D space. And that is orthographic or orthogonal projection. Okay, so that's orthographic projection. Orthographic projection. So we have OX here, and on the top, that's the frontal plane, front plane. We have 2 lines, and the bottom is horizontal plane, top plane, right? So that is AB and CD without any dashes, but they are lies on same line. Okay, so same straight line, and so if the lines are parallel in the 3D space, okay, in the 3D space, these A, B, and C, D are parallel. Okay, so these are parallel. So if in the 3D space the lines are parallel, on their projections also will be a parallel. Okay, so on the both or 3 projections they will be a parallel. Okay? In every projections they will be parallel. So here they are parallel, and here also are parallel. If one of them are not parallel, so then in the 3D space all those lines are not parallel. Okay, so that's a rule. So intersection. So in the 3D space, these intersected lines are given. These 2 intersected lines are given, That's the projection. That's a projection. So the rule is, again, if the lines are intersected with each other in the 3D space, so in their projections also they will intersect. Okay. If any of the projections they are not intersected, that means in the 3D space those lines are not projected. Okay, understood? Okay, I will repeat it. If the line in the 3D space, if the two lines in the 3D space, so these lines are intersected with each other, and if they generate kind of single point, K point, so in their projections, they also intersect. If, okay, so here in their projections, in every projection they will intersect. If the lines are not intersected in any projection, so that means in the 3D, those are not projected. So another thing is projection of right angle. So there is a theorem: a projection of a right angle with one parallel leg to any projection plane will be also right projected angle. Okay. If the right angle is given in the space, and if the one leg, one side, okay, so this one side is parallel to the any projection plane, for example P plane. Okay, so it's a parallel to the P, so that's why angle of projection, okay, projection on that plane also will be a right angle. Okay, so even though so another leg, it might not be parallel. For example, key E line is not parallel to the P, but only one leg, ED leg, is parallel to the P. The one leg is enough to be a to have a right angle. Okay, so in the space it has a 90-degree. So but if you project it, the projection, in the projection also, that angle keeps that angle remains 90-degree. Okay, so it's a right angle. So that's a theorem. Okay, so only one leg is enough to be a right angle. Okay, so one leg should be parallel with given projection plane. So this thing we can see here. Okay, in one projection it's a 90-degree, but in another projection, so if you see from this side, if you project it to this plane, so you will have something like this. Okay, so one leg is ED is here, and KE is here, like this. So this one. So if you make okay, if in another projection, so front projection, if in one projection is 90-degree, it will be in any projection 90-degree, but others might not, if it's not parallel. If that is in two legs are parallel, so then in one projection it will be something like this. So A will be here. Okay, A, B, C. In one projection it will be a line, and in another projection that will be that will have a 90-degree or right angle. So we use this information. Okay, so one leg is parallel, so then that will keep that angle. So we'll use this information. True length of a projected line. Okay, so there's a theorem, another theorem. The true length of the line is equal to hypotenuse of a right triangle with one leg is a projection in any projection view, and another leg is difference of lines both points position from projection plane. Okay, so true length means in reality, in a 3D space, it has a the length, right? So the distance from A to B, that is absolute distance. Okay, so real distance is AB. But in the projection, if it's given like this, So both sides has a slope. So AB and AB has a slope. So we don't know the real true length. Okay, so exact length. So by here, so you have to see in order to measure the distance, you need to see from perpendicular. Okay, so from 90 degree. So then you can measure it. So how to make a true length, or how to make it 90 degree when you have in both projections has a slope. Both projections are not the view is not 90 degrees. So we have to make we have to measure the distance between. Okay, so between A and B. So we need to calculate that distance, or we have to make get that distance. Then in another projection, we need to make 90-degree line. Okay, so we will make this line. So green things are given, so we have to find red one. The 90-degree line, which is perpendicular to the green one. Okay, so then put that distance here, find this BO point, B0 point, and then from another end, from A point, make the line, so red line. And then so this one is true length. In the opposite way, second way is you can get this distance, so make a straight line, get this distance in any end of this line, create a perpendicular line, and then put that distance there, define at A0 point, and then connect this A0 point and another end of the given projection line. So that is a red one is true distance, true length. Okay, so the way is like that. So in reality, something like this. So we have AB, so we have this one. This one is generated from AB, right? So that's why the length of this one is equal to the this one is taken from here, and we are making 90 degree on that plane. So we put there that distance, this distance, and then we are making this AB one. So same like if we rotate this one and we put this one to the side. Okay, so the B is here. Okay.
Projection of straight line. Example number 1. Today, let's explore the projection of a straight line, focusing on a special case where the line is tilted to both vertical and horizontal planes. Remember our last video about different line positions in orthographic views? We're going to concentrate on that last position we mentioned. This case is important because it's common in many problems. Here's the challenge. When we look at the line from the front or top view, its real length isn't clear. So, how do we figure out the actual length? That's what we're going to learn in this video. Get ready to discover the method to find the true size of such a line. Let's get started. Before we dive into the method, there's something important we need to understand. When we're looking at the line in the front view, we represent it as A dash and B dash. In the top view, the same line is shown as A and B now. Imagine a line that goes from A dash in the front view to A in the top view. This line is what we call a projector. Similarly, there's another projector that goes from B dash to B. These projectors are key to understanding how the line is positioned in space. Keep this in mind as we move forward. Now, let's tackle how to find the true length of a line that's inclined to both the vertical and horizontal planes. If our line was inclined to just one plane, we'd easily see its true length in one of the views. For instance, imagine this line parallel to the horizontal plane. From the top view, you'd clearly see its true length. Similarly, if it were parallel to the vertical plane, the front view would reveal its true length. Keep these images in mind as a reference. When the line is parallel to the horizontal plane, we get its 2D representation like this, and similarly when it's parallel to the vertical plane. Notice how the endpoints of both the actual line and the tilted line align. So, how do we find the true length in a 2D view? Let's explore. Our top view shows the line inclined to the horizontal plane, appearing angled in the front view. Rotate this line to make it parallel to the reference line. Start by drawing horizontal lines from each endpoint of the line. Remember, the endpoints of the original and the imaginary tilted lines align horizontally. Then, use a compass, set to the length of the line in the front view and draw an arc. Extend this line downwards to find the new endpoint. Let's call it B1. The intersection point here is the end of our tilted line. Then, draw a line from point A to this new B1 point. This line represents the true length. When we adjust the line to be parallel to the horizontal plane, the imaginary line's inclination changes, showing the angle it makes with the vertical plane, which we'll call phi. For the true length when the line is parallel to the vertical plane, draw a horizontal line from the endpoint A. Adjust a compass to the length in the top view and draw an arc as shown. Extend it upwards to find the other end of the line. Draw a line from point A dash to this new point, which we'll call B1 dash. This shows the actual length of the line. The new angle it makes with the horizontal plane is represented by theta. This is how we find the true length of a line, which is inclined to both the vertical and horizontal planes. Important key points to remember are vertical alignment of endpoints. The endpoints, A dash and A, as well as B dash and B, are aligned vertically. This alignment is crucial for accurate projection. Horizontal line and locus. The endpoints of the actual line and the imaginary tilted line lie on the same horizontal line. This horizontal line acts as the locus for points B dash and B for the line. Naming of views. It's important to carefully note how the front and top views are labeled, with a dash for the front view and without a dash for the top view. In future
Today, we are going to learn about skew lines in geometry. Unlike so many shapes in geometry, skew lines live in our world. They are part of the geometry of 3 dimensions, just as you and all your friends are 3-dimensional beings. Skew lines can only exist in 3 dimensions. They cannot be part of the 2-dimensional world of polygons and circles. What are skew lines? Skew lines are lines that are in different planes. They are never parallel, and they never intersect. On the other hand, parallel lines are lines that are in the same plane and never intersect. In other words, parallel lines must exist in 2 dimensions. They are parallel within the same plane. Skew lines cannot exist in 2 dimensions and are always in different, non-intersecting planes. Remember that in mathematics, lines continue in both directions forever. Suppose you wanted to build a big wooden box to hold line segments. You would find the longest line segment and make the box slightly bigger than that, right? What if, though, you wanted to hold rays or lines? No box exists that could hold either, because rays continue in one direction forever and lines continue in 2 directions forever. Skew lines are what you would have if you tried to store lines in a big box, like a bunch of infinite double-ended arrows. They would not cooperate. Skew lines have several identifying properties that make the big wooden box impractical. They continue in 2 directions forever. They are in different planes. They are never parallel. They never intersect. Let's take a look at some examples of skew lines. Please step into our imaginary geometry elevator. An elevator is a rectangle prism. 6 faces, 8 vertices, 12 edges, and so on. The inside walls are all dry erase boards, and you happen to have a dry erase marker and a straight edge in your hands. So you draw a line on the side wall of the elevator, stretching from the top of the elevator car to the floor, complete with arrowheads. That looks nice. So you draw another line on the opposite side wall, going from the car's front to back. Notice the 2 lines are in 2 separate planes, separated by all the space you are occupying. More, one line is going up and down, while the other is going front to back. Those are skew lines. They are not parallel, and they will never intersect. They are in two different planes. Inside the elevator, you realize you are looking at 12 edges, where planes intersect. You have 4 ceiling edges, 4 wall edges, 4 floor edges. Select any edge, then select another edge that is 1 not parallel to your first edge and 2 does not share either plane that created the first edge. Do those two things, and you have found skew lines. Next, we have diagonals. Since skew lines must exist in three-dimensional space, you can include diagonals in your search for skew lines. A line cutting diagonally from one corner of the elevator ceiling to another corner of the same ceiling is skew to the 4 edges of the floor. Lines, line segments, and rays can all be skew. You can perform a quick check of suspected skew lines just with your straight edge. Align it on one line and physically move it to the other line. If you have to twist, turn, rotate, or otherwise change the orientation of your straight edge to align with the second line, then the two lines are skew.